Good afternoon, everyone, and welcome to Chase Plastics Chase the Knowledge webinar on electric vehicle thermoplastic solutions. My name is Sherry Cudd, and I'm the Advertising and Marketing Manager for Chase Plastics. Thank you all for your interest in this webinar and for taking time out of your day to attend. A few quick housekeeping items before we begin. Everyone except the presenter is on mute and will be for the duration of the webinar. But if you'd like to ask a question, you can do so at any time by typing it in the questions section of your toolbar. If you'd rather ask your question verbally, please raise your hand in the toolbar and I will unmute you and call on you to ask your question out loud. If your question does not get answered right away, we will address it at the end of the webinar. You can access and download PDF copies of the presentation, our product line card, our automotive one-pager, and information on our technical engineering team in the handout section during the presentation. And you'll see that section right below the questions section. If you are attending live, a certificate of completion and recording of the webinar will be emailed to you about an hour after the webinar concludes. You will receive a separate email from Jason Merkle, our presenter, with a PDF of the presentation and handouts. We would greatly appreciate it if you could complete the survey at the end so we can improve future webinars for you and cover the topics that interest you most. We encourage you to check out past webinars and recordings on the webinars page of our website at chaseplastics.com/webinars. If you would like a custom Chase the Knowledge presentation given to your organization discussing a specific topic or material, please send an email to your presenter, Jason Merkle. Our entire sales and technical team are always ready to assist with technical issues, material selection, and educating you and your team on products and processes specific to your needs. Future Chase the Knowledge webinar announcements will also appear on this page. You can now subscribe or invite coworkers to subscribe to receive notifications of all future Chase the Knowledge webinars on this page as well. Another great technical resource is the Chase the Knowledge blogs on our website. There are currently 9 live topics, including one on EV shifting requirements for plastics, and they can be found at chaseplastics.com/blogs or under the resources tab from the homepage. And if you're in the injection molding, if you're at the Injection Molding and Design Show in Novi, Michigan come September, stop by our booth and say hi. You can meet Jason. At this point, I'd like to hand it over to our presenter, Jason Merkle. Jason is the technical manager here at Chase Plastics and has been with us since 2012. He received his bachelor's degree in plastics engineering technology from Ferris State University and his master's in plastics engineering technology from the University of Massachusetts Lowell. For those of you who have attended Chase the Knowledge webinars in the past or contacted our technical engineering team for assistance, you're very familiar with Jason and the level of expertise he brings to the table. So without further ado, Jason.
Thank you very much, Sherry. And thank you everyone else for joining. I look forward to a fruitful conversation today. As you know, we're here to talk about electric vehicle solutions and the plastics that go along with those types of applications. You can see on the screen here just a brief agenda of what we plan to cover today. EV market trends, the changes in technology that are prompting a shift in the parts that we see used in the vehicles. Battery brief overview from a very high level, flame retardant standards and updates, some of the applications we see driving change within the EV space, materials gaining traction in EV as a resultant of those changes, and then time for discussion and questions at the end, as Sherry alluded to. So to get started, just a brief snapshot here of what we're looking at in the United States in regards to EV adoption rate. This is all relative to sales of vehicles here in the US, of new cars specifically. And while it looks a little low in comparison to the overall number of vehicles being sold in the US, we are getting closer To that 10% mark, you can see 299,000 vehicles sold in the EV space through Q1 of this year, with all indicators showing that we should pass about 1 million EV cars purchased in the United States yet in 2023, which would be a record of its own, with the expectation that this will likely grow as automakers domestically and abroad continue to shift their focus to EV vehicles and lowering the carbon footprint. On a similar note, from a plastics perspective, this is the growth that the United States is expecting from electrical vehicles and plastics use overall. Now, looking at the slide, obviously, there's quite a bit of business potential growth from 2020 out through 2030, most of that aligning directly with the amount of vehicles being produced in the EV market, not necessarily looking to quadruple the amount of plastic used on a vehicle, although that would be nice for most of us in our businesses. But the overall adoption, as there's more and more EV vehicles on the road, we expect the volumes of plastic used per vehicle to increase accordingly. So maybe no surprise that the materials outlined here, from polypropylene, olefins in general, TPOs, compounded propylene, and things like that. PBT use in connectors, polyethylene, PCU. So, all the usual suspects from the materials being offered and used in the electric vehicles. Polyurethane you see in there is a rather big segment that's primarily related to foams and seating, more so than thermoplastic urethane. But promising growth in this market, and why we're also engaged with staying on top of the cutting edge of what the technology offers, both from a plastics perspective and what it can do for the vehicle. So what's really driving a lot of the changes we're seeing in the plastics market? This is a very high-level overview that we'll dig into a bit of each of these as we continue through the presentation. But obviously, flammability is a big one, common to anyone who's seen the news about electric vehicles that have caught fire in the past, and how that's changing with newer technologies, and what both automakers and us who help produce plastic parts can do to help mitigate that. So flammability requirements are driving tremendous change within the vehicle in a way that's different from what we've seen historically with internal combustion engines. Battery acid and electrolyte exposures, obviously each battery type from each manufacturer has its own special sauce, so to speak, within the cells, which we'll get into a little more specifically in the coming slides. But both intentional and unintentional exposure to battery-related fluids is a growing area of interest and concern. Impact energy management, how do you protect a battery system when you're in a collision? Obviously, both in internal combustion and EV battery type vehicles, impact energy management is important, but with the livelihood of the vehicle being spread across, the bottom of the chassis and a lot of the EV structures, we are looking at different ways to manage energy from impact to both keep the passenger safe as well as prolong the life of the vehicle itself. Changes in environment temperatures, not specifically the external environment around us, but more so the environment under the hood, temperatures that we're seeing both higher and lower compared to traditional combustion engines, and how we can navigate the material selection process to take advantage of certain aspects of that, whether they be increasing or decreasing temperature thresholds. New aesthetic and interior resistance needs as we look towards electrification, and then ultimately the potential for more autonomous driving down the road. How does the scope of what a passenger does and how they interface with the vehicle is expected to change as well? If you don't have to have your hands on the wheel constantly, we're seeing a lot of changes to interiors already, even without being exactly on the precipice of full autonomous driving. But that is giving us some flexibility and new challenges, both good and bad, in how we choose materials for the interior of the vehicle. Charging infrastructure, obviously this is a very big conversation as we look to adopt EVs more fully here in North America. The amount of range, the number of charging stations, the type of charging stations, the accessibility of, will one OEM's charger work with another's, which is, being updated nearly constantly as they continue to see what the future looks like for EV development. So that's a big part of the discussion as well. And we'll focus on charging stations and the requirements specifically later on in the presentation. High voltage cautions, we're dealing with voltage that's not traditionally common to vehicles if you were to look 5, 10, 20 years ago. So how do we handle those high voltages in terms of an installation perspective with plastics? How do we notify the consumer or the OEM or the mechanic as to what components are under high voltage and which are not? So that is complicating the scene as well. Range extending capabilities. At the end of the day, we're always looking to have these vehicles go as far as they can, much like gas mileage traditionally. So what can we do with polymers to extend the range of a vehicle? Most of that is related to lightweighting, amongst other potential benefits, but we'll dig into that as well. And then the end of life, the warranty for the vehicle, the warranty for the battery, the cost to replace. How do we manufacture these systems or assemblies in a way that they are replaceable or recyclable? Continues to be a challenge to the industry as we look at more full adoption of EVs across the market. A high-level overview of battery terminology, just so we're on the same page as we start to talk through some of the applications. This is the rough breakdown of your traditional battery used in EV. Very, very rough breakdown from a high level, but the battery cell itself, this is the basic unit of the battery, as it says here. Cylindrical, not that different from in nature the batteries you may have at home from a AA or a C or D, just traditionally much bigger and much higher output compared to what we're used to at home, since they need to power the actual vehicle. You'll see the term the chemistry referenced on occasion. This is the combination of the anode, cathode, and electrolyte that are used in the battery cells themselves. So what within that cell causes the battery to function. Every OEM or battery producer may have their own flavor, so to speak, in terms of the chemistry that goes into their battery cell, allowing them to have slight advantages relating to range or charging speed or temperature of operation, what have you. Battery module, this is an assembly of battery cells into a frame. So you'll take a certain number of cells that is rated for a given range or voltage and put them into a module. And then several modules can be assembled into what's known as the battery pack. This is the final system that gets installed into the vehicle itself. And then along with the battery pack, you'll typically find two management systems, one being the battery management system that handles most things related to electricity and temperature. So voltage, current, temperature, these allow the battery to operate at its optimum performance while also providing some protection to the user or passenger should there be a high voltage runaway or an issue with the battery cell to potentially cut off power to the battery and separate it from the vehicle itself. And then finally, the battery thermal management system, as you can see here, maintains the temperature of the powertrain cabin and other systems of the EV. So equally as important as we look to control things like thermal runaway, which we'll talk about in a few slides as well. So that's the overview from a terminology perspective. Moving onwards, we're going to do a rough breakdown of the batteries in greater detail to show you what some of those terms actually look like. So in terms of batteries used in the electric vehicle market or other markets as well, traditional internal combustion engines, you can see below the different types of batteries that are being used. So no surprise to most of you, I would imagine lithium-ion batteries are the most widely used type of batteries in electric vehicles. We do see some nickel metal hybrid type batteries used in hybrids because they have their own advantages in terms of spacing and level of expense. But so far, in order to get the range and output that we're looking for a truly independent EV with no hybrid technology, lithium ion tends to take the crown there. Lead acid batteries are obviously still around, as you've seen in your combustion engine vehicles, as well as boats or other off-roading type equipment. Those will continue to be around for a while, but don't have quite the technology to power the vehicle independently. And then we see the use of ultracapacitors as well for secondary storage and to provide extra power. So that's the rough breakdown of the batteries overall in EVs. Our focus is going to be on lithium ion from here on out in terms of the presentation, and seems to be the way that the market is trending and plans to stay for the foreseeable future. The battery structure. So the module, which I mentioned earlier, it contains all the cells. So you can see here the individual battery cells that are aligned and arrayed throughout the module. So the module functions to protect the battery cells, support them, cool them, and connect them from an electrical perspective. Typically, you can see anything from just tens of them to thousands of these in an array, depending on the size of the vehicle, what type of range you're looking for, the overall voltage that the battery pack itself plans to offer. And you'll find that this differs in terms of layout, size, number of cells and packs, and the overall number of modules by OEM. You know, if it's a smaller car with lower output, obviously we would expect a lesser number of cells and corresponding modules. Larger vehicles that are functioning on a platform, like a skateboard platform for the battery itself, where you have the battery lining basically the full floor of the vehicle, those would have a tremendously higher amount of cells. Also, the size of the cell matters over the same footprint in the vehicle. Smaller cells, you're obviously going to have more of them, larger cells, lesser, and it's a balance of output to the number of cells that is struck by each OEM based on their expectations for range, acceleration, and things like charging speed as well. The pack itself, in the bottom here, you see an image. So these would be all the individual modules that are aligned and assembled together before being placed into the vehicle. They can be super heavy. You can see here upwards of 1,000 pounds, which represents basically a quarter of your vehicle's weight. And the most common voltages we see are between 400 and 900 volts overall. So you see in this image specifically, more of kind of the skateboard complex in terms of how the batteries are being deployed and installed in the base of the vehicle. Thermal runaway, it's a term you might have heard before, one that we hear pretty commonly in the EV space, but it also applies to lithium-ion battery usage and other things like portable electronics, cell phones, what have you. But thermal runaway, as you see here, is a risk relative or related to lithium-ion batteries, where the lithium-ion cell enters an uncontrollable self-heating state. So basically, lithium-ion cells are the process of charge and discharge is normally accompanied by a small amount of heat that is dissipated through the cell. When a battery cell, enters thermal runaway, the lithium-ion cell generates heat at a rate several times higher than the rate at which the heat can dissipate from the cell. So you basically have runaway power heading into the cell to the point at which it overheats and eventually will typically combust. As you can see here, that it can result in ejection of gas, shrapnel, other particulates that are held within the battery, extremely high temperatures, smoke and fire. And then once that fire is started in a vehicle, it can be very difficult to put out. Obviously, this is a big concern in electric vehicles among anything else that uses a lithium-ion battery. There are ways that the industry, both the OEMs and the plastics producers, are working to prevent this or control this, which we'll talk about to a greater degree, but it primarily comes down to flame mitigation, flame retardants used in plastic. How do we make sure that the battery is appropriately insulated from the vehicle? Do we have guards in place should there be any sort of thermal runaway with the combustion that's happening for ejection of gas or shrapnel to prevent the passengers? All of these are providing new challenges to the market in a larger way than we've seen ever with combustion engines. So UL has been working to establish some new standards for measuring thermal runaway performance and overall flame benefits of certain products over others. These are not exactly an approval system, but more of a screening to see how long under certain environments a part or material type is capable of lasting. And we're really seeing the standards come to us in two different facets, so to speak. UL 94 standards are still referenced quite often, more so than maybe they ever were in the automotive industry prior to the adoption of the EVs. So UL, obviously, if you're familiar with them, you've heard of certain values like HV rated for horizontal burn, or V0 or V1, V2, or 5VA, all those in increasing levels of flame performance. Traditionally, those have been applied to a lot more non-automotive type applications. So things that are installed in your home, things that are installed in public infrastructure, personal electronics, anything wired within your home most likely has to adhere to some sort of UL standard. Well, in the plastics world, we've traditionally held that down to if you need a self-extinguishing product, you would need a vertical burn rated product, which would be a V2, V1, or most commonly seen V0 rating, which means it's going to self-extinguish and not drip enough to promote ignition of other sources around the product should it catch on fire, with 5VA being the step above V0. We're starting to see more V0 and 5VA UL94 ratings referenced on part prints within automotive, where traditionally that has not been part of the conversation, frankly speaking. In addition to that, UL has rolled out their new 2596 standard for battery enclosure material screening. So that involves the two tests that you see here. The image on top is the battery enclosure thermal runaway test. So they will take that metal chamber you see there and line it with battery cells, and then put the proposed insulating material as what you see kind of clamped on top in the lighter color. And then those battery cells held within the chamber are intentionally led to thermal runaway, with one combusting and then lighting the rest of the array. And all it's designed to do in this test is to show how the material being tested, whether it be polymer or metal or what have you, composite, how does it respond to the combustion? Does it catch on fire? If it does catch on fire, how long will it burn? Will it mitigate the flame at all? So it's just a means of putting the prospective part or material into a real life test chamber in order to see how it burns and how safely the material can be used should there be a thermal runaway type of situation. The second test involved in the UL 2596 is the torch and grit test, which you see in the bottom image, where they effectively take a torch, a blowtorch, and both flame and grit is blown at a sample piece. Again, this could be polymer, it could be metal, it could be something else. And all they're doing is simulating the combustion of a cell with the shrapnel and grit that can produce to see how well the polymer or other type of material being tested will withstand such an environment. So as you can see here, they're very rigorous tests, a little bit different from what we've seen traditionally for under the hood type of compliance, but it's starting to give us a barometer for how one material can compare to another in both thermal runaway and overall flame resistance. And we intend to see more and more of that coming from UL and the polymer manufacturers as time goes on as to how the materials stand up to both of these tests. I'm going to work through a couple different areas of the vehicle as to what we're seeing in terms of changes to parts, and then the corresponding materials we'll touch on later. Under the hood, as we move away from combustion engine, obviously with a large battery, there's quite a bit of voltage and current to transmit via wiring or alternative devices like bus bars. What does that mean for us in terms of plastic parts production? Well, you can imagine that all of your wire management is going to increase in both frequency of product used and overall volume of them used as well, as we look to move a lot more type of wiring through the vehicle, whether it be through the floors or along the doors, just transmitting voltage or letting each of the components communicate to one another as well. There's a lot more wires in an electric vehicle than your traditional internal combustion engine, which is probably no surprise to any of you. Cooling lines, how do we cool the battery differently from the ways that we cool the engine? This can differ in the amount of travel that the coolant has to flow as we look at a battery that spans the whole length of a car rather than, you know, an engine that's traditionally been held in the front or back exclusively. There's a lot more ground to cover. So cooling lines are changing. No significant changes in coolant type being used yet, but that is on the horizon as a potential change. And should we get away from water and glycol usage as a coolant, there may be some more chemical resistance challenges to tackle as we get down that road. But under the hood, we're certainly seeing an increase in both wire management, clips, fasteners, things of those design, as well as cooling lines. Bus bar assemblies is also an area that we've seen a tremendous amount of growth in within EVs. So bus bars, if you're unfamiliar, you know, they're basically a strip of metal that are encapsulated with a polymer or some other type of material. In the picture here, you know, most of the flat orange pieces in this image are bus bars. And all they do is act to conduct voltage from one area to other, much like a wire. But when you're dealing with high voltage type applications, wiring can get relatively thick. What a bus bar offers you is space savings over traditional wiring, where you may have had a 1/2 inch thick or 3/4 inch thick cable in order to conduct the high voltage. You can do the same thing with a much thinner strip of metal that's then encapsulated with a polymer in order to achieve the same function. the biggest critical to quality items that come into plastic material selection for bus bar assemblies are really come down to two for the most part. Thermal environment of the part, how close is it going to be to the battery, how hot do we expect it to get, and then is there an FR requirement for the material as well if we're fear that it's going to be near a ignition source or potential ignition source, so that should there be thermal runaway or some other catastrophic event. So a pretty wide range of materials being considered for bus bar assemblies, all the way from polypropylene and flame retardant polypropylene, all the way up to things like PPA, nylons, modified PPOs, PEI being considered as well, polyphenylene sulfide for its inherent FR. And again, in most cases, that decision is almost made for us by the type of temperature that we need to withstand and the amount of flame retardants needed and at what thickness. Other under the hood updates and changes, we're increasing the length and upper limits of thermal exposure within the vehicle for two reasons. One, as automakers and the OEMs focus to extend the longevity of the life of the vehicle, they want to be able to say that, yes, this battery is going to be able to operate at high temperature for, traditionally with internal combustion engines, maybe it was 2,000 hours. And then we expanded our testing to 2,500 hours of exposure, and then 3,000 hours of exposure. And we've raised the temperature at which we need to be able to withstand for certain polymeric parts. So those demands are not going away by any means, and continue to challenge not only the polymer types chosen for certain applications, but the heat stabilization systems, the long-term stabilization systems that we're seeing, to not only allow the products to last that long, but to last that long with as minimal dip in performance or mechanical properties as possible. We're also seeing a lot more flame retardant versions for under the hood items that maybe traditionally had not needed to be flame retardant. Again, this is all to mitigate risk related to the potential for thermal runaway, but parts that may have been a standard polymer under the hood before are now being transitioned to the flame retardant versions of those materials, or switched to a new polymer in general to help with the flame retardant performance. And that brings advantages in terms of mitigating flame spread, but also challenges in terms of mechanical performance, colorability, overall ductility of the polymer. So it's definitely a changing landscape for some of the traditionally used plastics underneath the hood. And then metal to plastic conversion under the hood, as well as elsewhere, remains ever as important, if not more important, than with internal combustion engines, because we are looking to fuel the range of an electric vehicle, which is heavily negated by the overall weight of the battery itself and the rest of the vehicle. So weight savings will continue to be a priority for OEMs in the EV space, just as much or more so than it was for the combustion engine space. Exterior innovations. Driver assistance systems. Most vehicles now are becoming more commonplace with some sort of sensing technology to help with lane departure avoidance, adaptive cruise control, parking assistance, emergency braking. All of this is managed by typically your ADAS systems, whether it be LiDAR, radar, infrared cameras, what have you. So we in the plastics industry, as you guys have seen, have needed to adjust the type of materials used to make these products as functional as possible, as accurate as possible, and to engage with the surroundings as smartly as possible. So you see things like infrared and transparent lenses and covers. This specifically applies to LiDAR camera systems that may be mounted in the front of your vehicle, on the top of your vehicle, some of them being mounted in the headlamp system itself. If you've got an infrared camera, you don't want the passenger to know that it's on, either from the exterior of the vehicle or the interior. There are ways to use certain dyes with a transparent material to allow for transmission of infrared waves, but that's invisible to the human eye. It would just look like a black part to you and I, even though it's actually transmitting light. And we'll get into that a little bit later as well. Innovations for accent and signal lighting. So more light pipes, more backlit displays, more backlit logos on the front of the vehicle, backlit grills. A lot of that is aesthetic for the time being, functional in some ways for low-level lighting, but we're also starting to have the conversations with OEMs and lighting manufacturers about human-machine interface, or HMI, so that by the time we get to the potential for more autonomous driving or fleet-related vehicles where you're taking an autonomous Uber, for lack of a better example, that the lighting on the exterior of the vehicle could be color-coded or convey messaging as to whether or not a vehicle is available, like the light on top of an old taxi cab. Is it available? Does it need to be cleaned? Does it need to be repaired? Is it safe to walk in front of a driverless vehicle? We're seeing those types of challenges in terms of external lighting in ways that the vehicle can communicate with its surroundings as well. As we've gotten away from the need for traditional radiators and the corresponding grills, obviously we've seen some design advantages and new aesthetics take off compared to traditional vehicles. So if you're looking at your average Tesla, obviously there's no longer a grill in the front, and that's providing opportunity to the OEMs to be more unique in how they design the front shape of the vehicle. Relating to the sensing technology that I mentioned, radar absorbing and blocking materials continue to grow in use as we put more sensors into the vehicle. The reason for that is many times, say a LiDAR component will have a wide array of the view of the LiDAR system, so to speak. So if you can see my cursor here, if you're looking at your blind spot monitoring system, you don't want that LiDAR functioning to tell you if there's anything within 360 degrees of that LiDAR sensor. You want it to be specifically focused on where your blind spot is. So we can use radar absorbing or blocking materials to kind of block all of the areas around that LiDAR system to make sure that it's only sensing within the scope or range of view that you want it to be accurate within. The more sensors that you put into the vehicle, the more need you may have for radar absorbing or blocking materials, not only to measure or encapsulate that scope of view that you want, but also to make sure that it's not giving you false positives for other areas of the vehicle. So should your LiDAR be able to see, or identify that there's a metallic component in your bumper, you don't want that setting off your blind spot monitoring or any other sort of safety related sensing. So radar absorbing and blocking materials, we anticipate growth as we put more sensing technology into the vehicle. And then finally, for exterior related innovations, battery management. How do we protect the battery as much as possible? That's being done through traditional metal structures now, but we're also, as we look at lightweighting, considering metal plastic hybrid components to help with energy management. And we've got quite a few presentations and specific materials of interest, should that be something you'd like to look into further down the road. But it's a rather complex conversation, but one that we'd be happy to have. Advances in lighting. These changes will be both related to the EV market as well as combustion engine, but I think it merits considering as we talk about new technology in the automotive market in general. So adaptive driving beams, also known as matrix lighting or DLP lighting, digital light processing, has now been legalized in the US. For the longest time, it was not legalized completely by the government locally, but has been used in Europe for several years. And what matrix lighting offers you is the ability to have selective lighting from the perspective of your headlamp specifically. So if you see the image down below, you can see that in a matrix lighting type setup, you're able to shut off or redirect certain areas of your headlight to where the image on the left would be your traditional conventional system where it's just pure light output. Image on the right using a matrix light system would allow you to get rid of glare to other drivers. So it would insulate, oncoming traffic or traffic in front of you from having any sort of heavy glare from your headlights, offering the driver to have as much high beam output as possible to identify surroundings without bothering other vehicles or causing safety concerns for other vehicles. So as those beams start to be implemented in the US, which is still being feathered out in terms of testing regimen and what it will take to get approved, that will further complicate the amount of technology, actuator systems, number of components that may go into a headlamp design, which brings its own list of complications in terms of thermal management. Are we going to have an increase of components or limited space within a headlamp driving the temperature up? How do we get that temperature out? How do we have materials that will be stable enough for use across a wide range of temperatures? So we're anticipating more changes to come as that technology continues to be adopted in the United States. We're seeing changes to sizing of internal headlamp components, both some getting smaller and some getting bigger. You know, bezels and reflectors seem to be downsizing as the overall footprint of the headlamp itself seems to be getting smaller. We're seeing that trend across most OEMs at this point. Contrary to that, light pipes and things that are providing more aesthetic details in some cases are growing in length. So they're going two different directions in some regards, but we've got polymers inclined to handle both of those, whether it be the heat or metallization of bezels and reflectors, or the high light output, high lumen output of light pipe type materials, where traditionally the challenge has been the longer the light pipe, the lesser light output you get, or less consistency of light, or less consistency of light color, as it tends to yellow as it goes down the light pipe. Engaging with new age materials, next gen materials, to keep those light pipes looking as crisp, clean, and consistent as possible. We're seeing, as I mentioned, increased complexity of systems being installed within the headlamp. So if you take your traditional headlamp and it's one or several bulbs, but also putting in a LiDAR sensor, an IR camera for parking or visual readings in front of the vehicle, radar. The more of those get put into the headlamp space, the more complexity we have in terms of dimensional tolerancing and thermal resistance, and we're engaging with polymers that are able to withstand that challenge. There had been a trend for a while in headlamps specifically that as we got away from traditional bulbs and more into the LED systems, the temperatures have come down and the need for high temp polymers has been somewhat negated over the past 2 to 5 years. And we've moved from things like thermosets and Altem down to high heat polycarbonate and all the way down to standard polycarbonate and PBTs in some cases. Well, this is starting to push the trend back the other direction, where you may need a higher value product with better dimensional stability, better light output, better structural rigidity at the end of the day to make these products that frankly put a lot of cost in your headlamp system, make them as functional as possible and as efficient as possible. So the CTQs, the critical to quality aspects for most of these lighting changes has been back to high heat resistance, the dimensional stability, low outgassing. Obviously, you don't want to have any internal fogging of your lamps, mechanical property retention over a long timeline, and then temperature management and conductivity. Should there be a need to remove heat from an assembly, how can we do that via either active air management or using the thermal conductivity of a polymer to assist with that? Interior related updates. As I mentioned, as we look to autonomous driving and how that can reshape the vehicle and the needs of how the passengers interact with the vehicle, it gives an open door to material changes for what can be used. So much more aesthetic type uses. We anticipate someone engaging with things as simple as the dashboard differently than they did before. So if you look at the new Grand Wagoneer, and now there's a screen that stretches all the way across the dash and in front of the passenger for them to use. It requires different materials than what we've looked at traditionally. So high gloss areas, low gloss areas, customer preferences to what they'd like to see within the vehicle itself is all changing. And then you see different changes with EVs. When you don't have the road noise or the engine noise specifically, every little buzz, squeak, and rattle becomes a lot more apparent. So we're looking at a number of things to help mitigate that. Obviously, you want to choose materials that mate together as best as possible to mitigate any potential for squeak, both in terms of the design and the polymers being chosen. In the instances where, hey, we built an assembly, we've got a squeak problem, what can we do to adjust it? Most often, we're looking to some sort of lubricated product in order to get past that squeak. So anything from the various different lubricants that we can put into polymers themselves. At times you'll see felt tape used or something to provide a cushion, for lack of a better word, between two mating components, but that can be costly. We're seeing more materials come to the market and being sold into applications to reduce buzz, squeak, and rattle, especially in EVs where they're much more easily identified. Finally, for this slide, passenger sensing technology has come quite a long way. You may have this in your vehicle if you have a minivan or anything with a third row, that when you go to get out of your car, on your screen up front pops a warning, hey, make sure you didn't forget anything in the back, especially if it's your dog or a child or something. And some of those systems are now accompanied with an infrared camera that is mounted in the roof of the vehicle to basically identify passengers from a thermal perspective. That's also being used in they call some of the family cams for the same reason, that if I'm driving down the road, say we're taking a family trip down south of Florida or something, and it's 11 o'clock at night, and I want to check on my kids in the back seat without turning on a light, I can use the infrared camera that's mounted in my ceiling so that they won't see any of the light coming through the camera, but on my screen up front, they're all highlighted and I can see my kids just fine. So putting that sensing technology not only on the front of the vehicle for collision avoidance and such, but into the interior of the vehicle for ease of use and better monitoring of your passengers is on its way up as well. This could parlay itself into more driver monitoring systems for autonomous vehicles or partially autonomous driving to make sure that, you know, a driver is attentive, awake, hands on the wheel kind of thing. So sensing technology may be further used within the interior of the vehicle as EVs continue to roll out. Charging station applications, these differ obviously from the CTQs that are involved with the vehicle itself, but as we look to see more and more chargers installed throughout the country, the number of companies trying to produce such applications and ideally some parity across the OEMs as to how these are deployed and what type of attachment connectors they use. We expect this to grow and be more fully vetted as more of them end up produced and installed. As you can imagine, the many different parts of a charging station all have tremendously different requirements. I put the really basic ones here in terms of what we're looking at as we're selecting materials for the charging station, both exterior, interior, and displays. The housing, as you can imagine, UV stable. Most often we want it to be colorable, chemical resistant for, you know, all the things that Mother Nature can throw its way, impact resistant should someone, God forbid, back into one or drive into one. So we want it to be stable, as aesthetically pleasing as possible, since many times these are being mounted in commercial spaces just as much as personal homes. The display itself, clear obviously for display. We need to be UV resistant. You don't want it yellowing over time. Impact resistant for the same reasons as the housing itself. And at times we're seeing the need for flame retardants compliance as well, typically with UL standards in this case, most commonly being the V0 rating or 5VA. The internal frame and console most certainly almost always have flame retardant requirements, as they are the ones adjacent to most of the electrical system or high voltage areas. You need the structural rigidity here. You know, it's what holds up the charging station itself and all the corresponding components. High voltage, so we want even beyond just having a flame rating for UL94, there are CTI values that we need. Is there certain dielectric strength or resistance that we're looking for in order to meet the best throughput of the electrical advantages of these charging stations? And then finally, the connector, you know, the piece that actually plugs into your car, needs to be flame retardant. We got a lot of voltage typically flowing through those, and you don't want that to be the source for any sort of ignition. Many times these also need to be UV stabilized, colorable, chemically resistant in a way that even is different from the housing. Because should you drop these on the ground, who knows what sort of puddle of automotive fluid it may fall into from someone who was there previously. All of Mother Nature's aspects, greases, fluids, things like that. So chemical resistance is a big one here. And then design is becoming more and more popular topic as we look to have some commonality amongst the OEMs in terms of how they can charge. How do we get a Ford or a GM vehicle to be able to charge on the Tesla supercharger? And most of that's being worked out at a very high level amongst the OEMs, somewhat in concert with the government, but that will continue to have effects on the materials that we choose based on the design and how it needs to interface with the vehicle during charging itself. So emerging materials. The landscape is shifting a bit as we look at EVs and the polymers that are deployed there. In most cases, we don't have brand new polymers coming out specifically to be used in EVs, but we are shifting from materials that maybe were used consistently outside of automotive before are now being employed more often within the automotive space. The items listed here are certainly not the only ones being used in the vehicle, and at times not even the most prominent ones being used in the vehicle. But as we shift to EVs, these are the biggest changes that we've seen, either in type of material used or frequency or volume that those materials are being used. So flame retardant nylons, whether it be nylon 6, nylon 6,6, long chain nylons, aromatic nylons, very much increasing in usage primarily under the hood or battery related applications for things like insulation, connectors, housings. You still get all the advantages of nylon being high temperature resistance and corrosion resistant. We're looking at relatively new age heat stabilization systems, moving away from copper halide and moving into organic based heat stabilizers for the sole reason of playing nicely and preventing corrosion when it comes to the leads that are in a connector system, which we're seeing a lot more of those used obviously in electric vehicles as we look to transmit power. Pre-colored orange has become a thing now, a primary indicator orange rather than a full color match, but some way to know that, hey, this connector or this system is enveloping or attached to a high voltage system, and we need to exercise caution as a resistance. See new innovations and need for PPA materials like Amidel or other materials. Primarily the increase in CTI is really helpful with this, variant of the nylon family, getting all the way up to 600 volts. As we continue to push the voltage held within an EV assembly and a battery assembly, the connectors and things that transmit that energy and power are going to need to be capable of withstanding the voltage. So traditionally, UL CTI testing has only gone up to 600 volts, which is why some of the PPAs and other materials we're looking at are rated to 600 volts. We're anticipating new testing standards may be needed in the future to start handling and testing capability for polymers to withstand well beyond 600 volts, instead of that being the threshold as it has been in the past. New PPAs have also been rolled out, specifically from Amidel, from Solvay and their Supreme line, with TGs all the way up to 165C. So pushing the bounds of what kind of thermal performance those type of products can offer, and giving them more opportunity to play in the EV space. PPS, polyphenylene sulfide, has always been used traditionally in a lot of electronic related applications, both in automotive and outside of automotive, for things from coils to bobbins, connectors, and what have you. PPS has excellent flame retardant capabilities. It is inherently flame retardant without any sort of additive needed. So that makes it a big play within the EV space, obviously, as we look to negate any sort of flammability risk. Very high temperature resistance and superb chemical resistance to most automotive fluids, both at room temperature and at elevated temperature. So typically the heat that's driving material selection in connectors and bus bars assembly many times is pushing us towards PPS or other high temperature variants as well, like a PEI or something similar, in order to withstand those temperatures, flame retardant requirements, and balance of chemical resistance needs. As we look at the changes to exteriors, highly weatherable polymers continues to be a mainstay. That's not that much different from internal combustion engines. But we'll get into some of the variants here in a second that could need new materials differently from combustion engines. Modified PPO products like Naril for a lot of battery related components. So if you've ever used a PPO, they're very chemically resistant, very stable from a dimensional perspective, not terribly difficult to make flame retardant. They've got low moisture uptake as well. So for anything that doesn't see extremely high heat, but is battery adjacent or battery attached, we're talking battery trays for production, sidewalls, encapsulants, things like that. We're seeing a lot more opportunity for PPO in EV related applications than we had even seen. I mean, it's a commonly used material in internal combustion engines already, for anything from ignition coils to body panels to valve systems and things like that. Now it's just growing into another space within the automotive market. Infrared transparent materials for sensors and covers. So when I need my IR camera to work successfully or my LiDAR, you need your overall sensor assembly and specifically the lenses to be as accurate as possible. in terms of output and wavelength transmittance. So products like polyether imide, Ultem, PC copolymers, a variety of PC copolymers from Sovik Specialties are IR transparent, excuse me. Acrylic, other materials are all being engaged for IR transparency while being colored. So this is done typically by choosing a color package that's less based on pigment and more based on dyes in order to transmit infrared waves in order to read the surrounding environment. On top of that, IR transparency, dimensional stability over a broad thermal spectrum, again, is becoming more and more important as you need that pinpoint accuracy in a lens, and a relatively small lens, to not change how it transmits, not change its shape or soften or lose mechanical performance, what have you, as you adjust from freezing temperatures in the winter all the way up to when the car is running hot and the headlamp is at full operating temperature with all of its included components that are being jammed in there now, and be able to offer the same functionality across that range of temperatures. Flame retardant PVT, we're seeing continually used. You know, it's been a connector material for a long time in the E&E market, just seeing more adoption of it within the automotive market as we move to more flame retardant connectors and control modules and things of that like. And then everything you've seen traditionally on a vehicle is most likely still there. So the filled olefins of the world, glass-filled, talc-filled polypropylene, TPOs, PC ABS for interior type applications, painted components in TPO and others for exterior applications, all those are still around. So I don't mean to negate those, but the list you see here is really where we're seeing the biggest change in terms of what's being adopted in EV vehicles as we continue to monitor the trend towards electrification. Future headwinds and opportunities, you know, these are really the question marks. What does the future look like? How will charging infrastructure improve, both in terms of frequency of options and the output of those types of stations? How quickly can they charge? How often can they charge? Are we going to change the way the charging systems are deployed? Do we move to a battery replacement program rather than a change? There's lots of options being discussed and discovered throughout the market, so we're keeping our head up to stay in line with how that will adjust the needs of a polymer and how we engage with plastic materials. What do we do about limited supply and materials used for battery production, such as metals like cobalts and things being sourced across the globe? And how do we engage with polymers that are resistant to those materials and make sure that we're deploying the most efficient batteries as possible that last as long as they can? End of life reclaim issues is a big question mark as well, as to what do you do with a battery when it's no longer useful? If it completely dies, what do you do with it? If it runs out of its battery life, so to speak, what's the cost to replace it? Trying to make that as manageable as possible through the ease of assembly, the types of products used, and how well it can be disassembled in order to reclaim any useful materials from the interior of the battery itself. New outlook for sustainable products and implementation. Obviously, sustainability is still a big buzzword within the automotive industry, as well as across the globe, as we look to protect our environment and have lesser dependence on fossil fuels where possible. I think EV and it being on the cutting edge of, you know, new designs and redesigning traditional components give space for new sustainable materials to be considered where they might not have been traditionally, just because we stick to what we know, right? So we're seeing new opportunities for growth there as well, in addition to the efforts for lightweighting to help with range as well, to have less dependence on plastics in general. And then how do we protect and lengthen the lifespan of the battery-related components? This is related to the fact that your battery is on when it's driving, it's propelling the vehicle, but also when you're home charging, you need that battery, or want that battery, to be within a specific temperature range to allow for fastest charging, but also maintaining the lifespan of the battery, you know, when it's basically on, call it 100% of the time, on during use, on during charging, and how we choose polymers that are going to be able to have a lifespan that is commensurate with the expectations of the vehicle. So these are challenges and opportunities for us in the materials market to engage with products that are capable of handling the new challenges. And here at Chase Plastics, we're working to stay as close to automakers, part producers, and our suppliers, the material manufacturers, to be as on top of cutting edge developments as we can to be able to offer you materials that will fit and confidently work. That is the last slide from the presentation.
All right, Jason, can you hear me?
Yeah.
All right, thank you so much for your comprehensive presentation. That was great. At this time, if you have any questions, we have a couple of minutes left here. Please type them into the questions section or raise your hand and I will unmute your microphone. I'm going to read the written questions first and then call on and unmute anyone who has their hands raised. Right now, that looks like Kathleen Horton, Ed Chung, and Clifford Floyd. But let me get through these written questions first with Jason and then we'll call on you. So Jason, the first question is, and let me know if you want me to break this into a few different questions, but regarding the increase in electronics and high voltage equipment, how does the thermoplastics play a role in this area? How do we deal with electromagnetic interference in the EV vehicles? What percentage of the TP ratio used for EMI shielding in the EV or just the ratio? Let me know if you want me to break that up.
No, I think I got it. I mean, roughly speaking, and I'll speak from our experience only, which, may be a small percentage of what you guys see as our customer base. Generally speaking, we're not seeing a tremendous increase in the EMI shielding capabilities from the polymer itself. Now, I think that's for a few reasons that we've seen traditionally in both automotive and non-automotive applications for EMI shielding. It's not easy to make a polymer that conductive in order to fully shield. So unless there's a real design complexity or minimization of number of parts in assembly or something like that, where we're consolidating parts into one plastic part, rarely are we seeing a move to EMI shielding type of plastics themselves being chosen. Now, obviously that leads the automakers to look at other opportunities to shield, whether that be with shields themselves, metallic shields or other materials. But at least from our perspective, we haven't seen too many challenges on the polymers themselves to be EMI shielding. Now, that being said, there are grades out there that offer EMI shielding. They're typically highly filled with some sort of conductive particulate or fiber. And we'd be happy to discuss what those options are should there be a challenge for more EMI shielding from a polymer component.
All right, Jason, the next question is, what about PETs for EVs?
Yeah, PET could definitely be used, and it is already in some ways. So PET comes in a manner of forms depending on what type of part or fiber you're looking at, as you may well be in tune with. Obviously the PET being used in your water bottles that are clear and flimsy is much different from a highly crystalline filled PET compound that's really a high temperature, mechanically stable polyester. So I'll give you kind of both answers. So PET is being used very similar to PBT in connectors. The advantage that PET offers over PBT is a slight increase in temperature in most cases, temperature resistance, that is. But outside of that, when we look at things like sustainability and ocean waste reclaim, fibrous polyesters like PET are also being used for textiles within the vehicle. I'll be the first one to say that here at Chase, we deal with the injection molding or extrusion or blow molding, hard components 99.9% of the time. So I'm not up to speed on all the ways the PET is used from a textile or non-woven perspective. But when it comes to molded components in a crystalline PET, we definitely see advantages potentially within the connector space, housings, bracketry, very similar to where we see PPT deployed now.
All right, and we have a few hands raised. So first I'm going to call on Kathleen Horton. Kathleen, if you can hear me, I'm going to try to unmute you. It looks like you're self-muted, so you may have to unmute yourself if you still have a question. And that's for Kathleen. Kathleen Horton. Kathleen, if you still have a question, let me know in the question section because it's not letting me unmute you. It says you're self-muted. So let's go to Clifford Floyd. Clifford, I'm going to unmute you. You look like you're set to go if you can answer or ask your question.
Hey, Jason. One of the trends we're seeing in the automotive space with the rise of EVs, which I'm not sure if you hit on, but I didn't hear anything about it, is the use of polypropylene for cooling components. So in this case, fluid routing connectors. We've actually had several RFQs come into our company for battery cooling components that are utilizing glass-filled PPs. Have you seen this trend, or is this just something that's new and upcoming, and we're just on the front end of it?
No, you make a great point. And I didn't hit on polypropylene usage specifically, so you're accurate there. That is a trend that we're seeing as well. It is being led by the EV shift, away from internal combustion engines. It's strictly due to a thermal threshold of traditionally used materials compared to polypropylene. So where, in a lot of fluid management now, you'll see products. By now, I mean in internal combustion engines, you'll see, hydrolysis resistant nylons being used, nylon 6,6 in many cases, or PPAs or PPS. Those are all chosen for the combination of their chemical resistance and thermal resistance at the end of the day. Polypropylene is one of the most capable materials in the market from a chemical resistance perspective, but lacks some of that high-end thermal stability. So as we've seen temperatures come down in certain areas of the vehicle with the advent of EVs, propylene is certainly being more engaged in the connectors, quick disconnects, in fluid routing systems in general. So you hit the nail on the head. I would say that's maybe not industry standard yet, but certainly the way things are trending for EVs.
Thank you.
No problem.
Okay, we have a few more questions here, Jason. Is there a concern with PPA in terms of reduction or reduced insulation resistance at high temperature? PPA's IR drops drastically at temperature. And that's Ed's question.
The short answer is yes. It is a concern, not one that has ruled it out for consideration or successful use within the EV space, but understanding the deterioration of electrical properties when at temperature for all polyamide-based materials is something we want to understand early on in the development phase. So the counter argument to that is, as we see PPAs move up in their thermal stability in general, like the higher TG option that I mentioned earlier in the presentation with Amidel Supreme, that is helping to negate some of the loss of electrical properties at temperature. But the fact of the matter is that most polyamides will have some sort of reduction in those properties, which is why materials like PPS and PEI are still being used prominently in the higher temperature type areas of the vehicle, including in EVs. So yes, it is something to be aware of and something that we're concerned with as we engage in new product development. But knowing the limits has allowed us to deploy PPAs and other nylons into the space safely, as long as we understand their shortcomings.
Perfect. All right, that looks like maybe our final question. Again asked, any comments for PVC?
PVC, I mean, it's certainly being used, and as we look at things like wire management, wire coatings, things like that, I would expect that there's potentially more of it being used in a vehicle now. PVC is tough for a few reasons. It doesn't have great thermal resistance. It is somewhat of a no-no on some hazardous substance type lists. So the amount of it used in a vehicle has gone down over the years. I'll be the first one to say that I don't work much with PVC specifically, especially in automotive, so I probably don't have the best outlook for you, but I would anticipate it being around for a while, but we're not seeing leaps and bounds of additional PVC used in traditionally molded parts.
All right, perfect. Well, that looks like our last question. As a final reminder, please complete the survey at the end of this webinar. And if you enjoyed today's presentation, and how couldn't you, please go to our webinars page and subscribe so that you don't miss any notifications on any future webinars that we host for Chase the Knowledge. Again, we appreciate your time today and taking time out of your busy schedules to attend the webinar. We hope it was informative and a great return on the investment of your time. If you have any technical questions that didn't get answered today, feel free to reach out to Jason directly. You see his contact information on the screen. Thank you all for attending, and we hope to see you at our next Chase the Knowledge webinar.